And then just be mindful of the blinky. All right, I'm going to define something similar matrices. Now, the word similar is kind of ambiguous. Okay, so I want to actually bring up a different example of similarity because from a notation standpoint, a lot of times we use the same notation. And again, that can be confusing. Where have you heard the word similar mathematically before?
Triangles? Geometry.
Yeah, geometry. So shapes in general. What does it mean for two shapes to be similar? Well, let's use a triangle because that's a perfect example. So I have a triangle ABC, and then I have a bigger triangle, let's call it XYZ. Triangle ABC, now this is why it's somewhat confusing because the tilde symbol, depending on the context, means very different things. In logic, what does that generally mean?
Not.
Not, yeah. In other areas, it means other things. In a geometric sense, we use it for similarity. We're also going to use that symbol in this class because we're not giving logical statements. What this means is that every corresponding angle is congruent and every corresponding ratio is equal. Okay, so if side XY was twice as big as side AB, then side XZ is twice as big as AC, and so on. The simplest proof of the Pythagorean theorem simply uses two similar triangles. I can prove the Pythagorean theorem in 5 minutes just using similar triangles. It's a beautiful proof. But similar shapes, okay, there's some confusion always. And I teach discrete math, and we talk about words like congruence. And here's why it gets a little bit strange, because we use the same words in different contexts. When it comes to shapes, congruence, the symbol for congruence, by the way, is an equal with a tilde on it, which is kind of an odd symbol. And I see people use this symbol all the time. No, it actually has one meaning mathematically. It means congruent. It isn't used for anything else. In the history of the world, I looked. I'm actually that old, so I What is congruence? Think shapes. Yeah, clones, identical in every measurable capacity and every visual capacity. Now this is a statistical term. We say they're identical quantitatively and qualitatively. Qualitatively would be the visual, quantitative would be the measurable. It would be kind of like saying, okay, these are congruent. Not exactly. Why? They're the exact same size, but do they look different? Yeah, it's got writing all over it. Qualitatively, these are not the same. I can clearly distinguish them. Oh, so two shapes that are identical in every conceivable way. We say they are congruent shapes. In every measurable way. Now, when you're thinking simple geometry, two-dimensional shapes, there's not a whole lot of measurements. I have basically areas and perimeters. Three-dimensional, I have more, don't I? Area, I have surface area, I have certain measurements of perimeter. We usually call that like girth. It's kind of a weird one. There's volumes. There's all sorts of different things in every measurable capacity. Okay, I'm not even going to get into bigger, more complicated things, human beings. For two human beings to be congruent, what would they have to be? Clones. That's literally the definition of a clone. In every measurable way, down to the cellular structure, everything's identical in every way. Congruence has two symbols. It has an equal sign and has a squiggle. The equal means everything measurable. The squiggle would be everything visual. Okay, so if I drew a picture of a circle and I put it on the board, I have a picture of a circle on the board, but you don't know how big the original circle was. You see my picture. The circle might have been 10 miles across, but I took a picture of it. You have no concept of the size of that circle. But would we agree that no matter what the circle looked like, all circles look exactly the same? The only thing that might change is their size? Yeah, all circles are similar. Similarity geometrically, the simplest way of saying it's the same size and shape. Size is the measurable, shape is the visual. Okay, that's what it means. So congruence is same size, equal measurements, that's the same size, visual. Okay, these are not congruent. These are similar. If they were congruent, then it wouldn't be equal ratios, it'd be equal lengths all the way across. We say two matrices are similar and we use the same term, but we're not measuring things geometrically though. So I have A and B are n by n. So first of all, matrices have to be square before I can even discuss similarity. And from this point on, pretty much everything's going to be square. From this point on. We're not going to have any use of things that are non-square. They don't have to be non-singular. They just have to be square. We're going to deal with as many singular matrices as non-singular matrices. We say that A is similar to B. We're defining it right now. If and only if there exists, that's the backwards capital E, that's called the existential qualifier. It's a logical connective. We use this all the time in mathematics. It's good for you to know it. There exists means there is at least one. There's another symbol that means all, every. Does everybody know what that one looks like?
Upside down A.
The upside down capital A. That's called the universal qualifier. This is a strong, this is for everyone, all of them, infinitely many. Well, there's at least one. And that's, so this one's kind of wimpy compared to this one. I just need one. There exists P and P inverse. Well, obviously P must be non-singular if P inverse exists, such that, and by the way, does anybody know what the symbol for such that? I love using mathematical notation. That would be in set form, but in sentence form, it's actually that one. The backward element symbol.
Oh, I don't know.
In shorthand form, it's actually this one. In set form, it's the vertical bar, yes. Such that, I'm going to put parentheses. I can get from one matrix to the other by a multiplication of P inverse AP. And by the way, it would not have mattered which one I multiplied. I could have said P inverse BP is equal to A. Just one of them when I multiply by P inverse on one side and P on the other. Now, P inverse is exactly the same P inverse we've always used. That is the transition matrix from one basis to another basis. So that one we learned back in chapter 4, it's still the same P inverse. But now we're also going to throw in the P that goes with it. Oh my gosh.
Is that the inverse of P inverse?
Yeah. Well, if I'm going from non-standard to non-standard, both P and P inverse require a little bit of work. If I'm going from standard to non-standard, which is pretty much going to be now the way things are from here on out, the P matrix is trivial. The P matrix is automatic. What would the P matrix be? It'd be your simple vectors from your B prime, written as columns. Now, we'll do an example of that in a moment. Okay? This is the definition of similarity. Okay? And it has all sorts of cool, crazy properties. But similar matrices, like similar triangles, they're similar because they share many, many, many characteristics, but they are not the same. A and B are most definitely different matrices. It would be redundant to use the same matrix. Okay, that wouldn't really make a lot of sense to say, well, let me go ahead and use the same matrix. Well, yeah, a matrix is similar to itself, because if I chose P to be the identity matrix, then what would P inverse be? The identity matrix, and that would work, wouldn't it? So matrix is certainly similar to itself, but that's not interesting. We need things to be different. So, start from beginning to end. T is going to map R2 to R2. Let's say T of x1, x2 equals, I'll keep it simple, 2x1 plus 4x2, x1 minus 2x2. Okay? I'm going to give you a non-standard basis B prime. I'll do my favorite one. I like doing this one. I like choosing numbers that are easy to work with. Gotten lately. All right. What does that imply? Well, that implies that I'm starting with the standard basis. The standard basis is always the default. If you're not told otherwise, anytime you write a vector, okay, I have a vector here. I'm going to call it vector AB. Is it correct to say that this is A times 1, 0 plus B times 0, 1? So if B is the standard basis, which is kind of the universal norm that we go by, then can I say, and let's call this vector A, how about? Then can I say vector A is A, oops, vector A, oops, sorry, relative to the standard basis, I could write it like this. Oh, that's really ugly, sorry. Is that true? Boy, I just went to a lot of work to just say the same thing. Whenever you give a vector, it's implied that that's what it is relative to the standard basis. You'd have to say otherwise. Oh, I have to give you a non-standard basis and ask you to express it in terms of the non-standard basis. That's what we're going to do in a moment. Okay? Everybody okay with that? So that's where this is. So, this one is kind of boring. So here's what I would like to do. Let's find the standard matrix. And the non-standard matrix relative to basis B prime, which we'll call A prime. So the standard matrix A is relative to the standard basis. That one is easy. If I take the standard basis and I run it through my transformation and then write everything as linear combinations, it's the one I could have just read. Okay? So what is the standard matrix then for this problem? Just that? Again, if I took 1, 0 and I ran it through here, I would get what? If I took 1, 0, I would get 2, 1, which is 2 1 zeros and 1 0 1. So 2 1 would be the vector relative to the standard basis, which is sit right here anyway. And then I do the same thing with 0 1. You don't need to do it for the standard basis. You already know it. But now I want to find the non-standard matrix. So let me call this V1. I'll call this V2. I find it easier to label them. In the long run, it's a little less writing. Okay. So next thing we're going to do is find T of V1 and T of V2. Okay, so what's T of V1?
6, -1.
6, -1. What's T of V2?
-2, 3.
So -2, +3, good. Now what I need to do is write this as something times 1, 1 plus something times 1, -1, and then the same thing here. So C1 of these plus C2 of these gives me this. I'm not going to try to figure it out in my head. I'm just going to go ahead and set it up. So 1, 1, 1, -1, 6, -1. Okay? I'm going to go ahead and solve that with a matrix. This is easy enough. So negative this plus this, negative this plus this, negative this plus this. So I have -2 C2s equals -7, so C2 is 7/2. Okay, I'm glad I didn't try to do it in my head because halves are not the first thing we'd all think of, right? It'd be a little bit more work. Now with that, what's C1 then? 5/2? Now let's do a quick check here. So what did I say, 7/2? 5/2? Let's see, so 12/2 and then 7/2 minus 5/2 if you want. Nope, something more. Oh, I wrote them back, sorry. Right answer, I just wrote them in the wrong order. That's 5/2, that's 7/2, okay. So 5/2 minus 7/2, yes, that works. All right, now let's do the same thing for the second one. Well, that makes it easy because I only need to change this part. -2, 3. So negative, then negative, that would be 5. So -2 C2s equals 5, so C2 is -5/2. So if C2 is negative 5 halves, then C1 looks like it'll be positive 1 half. All right, so let's see if that works. Oops. Plus sign there. Does that work? 1 half minus 5 halves is negative 2. 1 half plus 5 halves is positive. Okay, cool. We did it right. I solved both of these. By the way, could I have solved these by using an inverse matrix instead?
Yes.
Let's say I had to do a whole lot of these. Let's say I'm doing this several times over. I'm giving you a whole bunch of different vectors and you're doing this over and over. This is not long. Do you agree? Would using the inverse be faster? Actually, yes. Using an inverse to solve this, once I had to do it more than once, would have been way faster. Because I do the one multiplication and I'm done every time. There's no algebra to solve, I just multiply. I want you to keep that in mind because we're going to look at that when we look at this problem from a different point of view. That I could have found the inverse of my coefficient matrix and then took that and multiplied it by this to get my answer, multiplied it by this to get the other answer. In a 3 by 3, that is actually how you're going to do it probably most of the time because it's actually much faster. But finding the inverse takes so long. Maybe. Maybe. Not automatically. So, I'm done with this. This is my scratch work. So now let's state T of V1 relative to basis B prime. I'll write it as a column. 5 halves, 7 halves, because that's how it's going to show up in the matrix. It makes more sense to do it like this. We've mentioned this many times. Writing a vector in vector form or as a column matrix mean the same thing, but it's a context. When you have a matrix, you can't multiply the matrix times a vector. You multiply the matrix by another matrix, which is the column. There's no such algebra of literally multiplying by the vector, because the vector is not a matrix yet. So I have to make it a column. And then T of V2 is the second one. Okay. Therefore, I'll use a different color. My matrix A prime is so far so good?
Yep.
Everybody good with that? All right. Now, I would like to find P and P inverse. P inverse is the transition matrix from the standard basis to the non-standard basis. You could argue that P, therefore, you could think of as the transition matrix in reverse, and that would be correct. But it's extra work. You wouldn't need to do that. So how did we do the, okay? And it's understood in this problem that B represents the standard basis because B prime is my non-standard basis. So you remember how to do this? What goes first?
B prime.
B prime.
It's the vectors in B prime written as columns. Now the vectors of B written as columns. But when you're finding, or when you're starting with the standard basis, isn't the right side always going to look like the identity matrix then? So the steps you perform will be just the same steps you would perform to find a simple inverse of a matrix. But let's do it formally, because you're going to be doing this mostly with 3 by 3s. There's no shortcut. Yeah, we know there's a shortcut for 2 by 2s, but not for 3 by 3s. So, 1, 1, 1, 0. So negative of this, the negative of this, the negative of this. Now I'm going to take negative half of this row. And then the negative going the other way. So 1, 0, negative, negative. Does that look about right? Because I'm going from standard to non-standard, what is P?
The identity
prime.
matrix. The identity matrix?
No?
B prime. Or the matrix that we
Oh,
formed
yeah.
out of the column.
Think of it, look at this picture. These were the vectors of B prime, these were the vectors of B. If I'm doing the transition matrix in reverse, then this would be the left side, this would be the right side. Agreed? And I'd be done because the left side's already the identity. Does that make it easier? You go, oh, so what is P? Gosh, P was the ultimate gimme. P is 1, 1, 1, negative 1. It's the vectors of E prime as columns. Again, only because we're going from standard to non-standard. We've done this in the past from non-standard to non-standard, and it was a lot of work. And we did it that way so you saw all parts of the puzzle that were necessary. So now, if we're starting with the standard basis, half the work is literally gone. Wonderful. Now, just for fun, because that is our ultimate goal in this course, I would like to perform a multiplication. Okay? And the multiplication I want to perform, I would like to do P inverse AP. Should I write 1? Sorry, I can't say 2, 1, 4, negative 2. Now I'm going to get rid of this stuff because this is just, again, this was scratch work. Now when you're doing this, there is an order of things that make life, which should I multiply first?
The brace.
Yeah, the second two. No fractions yet. 2 plus 4, 2 minus 4, 1 minus 2, 1 plus 2. Huh. That's kind of strange. Have we seen those vectors before? Coincidence? Hardly.
Should not be negative 2 in here.
Did I lose one? Oh. Thank you, negative. Sorry. Is that right? Make sure, no boo-boos. Boo-boos are wrong. Okay, let's finish this. 6 halves minus 1 half is 5 halves. Negative 2 halves plus 3 halves is 1 half. 6 halves plus 1 half, that's 7 halves. Negative 2 halves, negative 3 halves is negative 5 halves. Again, I'm getting this overwhelming sense of deja vu. Are you guys feeling it too? We've seen this matrix before. Kind of important. Like, probably the most important thing we've done so far. Not the most important thing we're going to do, but the most important thing we've done so far. When I find the standard matrix and I find the non-standard matrix, they are, in fact, similar. And that is, by the way, that result is astronomically huge. That the standard and non-standard matrices are similar. Well, what's the P and the P inverse? Exactly the ones that are the transition matrices for the different bases. This would have been true if I'd been dealing with 2 non-standard bases. It's just the algebra is so much messier, and there's really no application for that one. So I'm not bothering with that one. I used to do that one all the time, and I find that, you know what, I'm wasting minutes. I'm going to do the stuff that you actually are going to do, which is always standard to non-standard. So very interesting. At the very least, it's very interesting. Now, I would like to know, is there another way we could have found these guys? We did it the old-fashioned way. We solved. Now, how hard was it to find P inverse in this case? In general, how hard is P inverse? We could be a bigger problem. Is P inverse hard?
Not too hard, but well.
if we're always starting with the standard basis, then finding P inverse is nothing more than finding the inverse of your original matrix. 3 by 3, 4 by 4. Excuse me. That, we know how long that takes. It's not a terrible process. But the advantage is if I find that matrix, then if I had said, what is this one right here? What is this vector? This is T of V1 relative to the standard basis, isn't it? So I'm actually going to write it this way. We said before it's redundant. We don't say relative to the standard basis, but in general, we don't always have to start with the standard. We can start with any basis and end up with any basis. And this is T relative to, well, literally the first basis. What if I took P inverse and I multiplied it by T of V1 relative to B? What is the result? T of V1 relative to B prime. That is the result. How do you know? Because it's sitting right here. Isn't that what you just did right here? P inverse times T of V1? That's what you got. So had I done this, now this is a huge piece of the puzzle. What does P inverse do? What is the point of P inverse? We did this way back in chapter 4. P inverse is the matrix that takes vectors relative to the first basis and writes them as vectors relative to the second basis. That's what we did way back in 4.7. You guys did this on the previous exam. We didn't have any need for it. We didn't have any application for it. It was a process. We're going to do this. We make this conversion. We don't know why. We're doing this. And it wasn't an exercise. No. But we just didn't have a goal in mind yet. So we were learning how to do something without a goal yet. I have a vector relative to one basis. I'm going to multiply it by the transition matrix and get a vector relative to the second basis, period. It's just that when I'm going from standard to non-standard, that makes it really simple, because if I was solving that system of equations that gave me these coefficients, it was equivalent to doing this multiplication. That's why I said doing this would actually be faster in general. Yes, it takes time to come up with P inverse. Let's pretend this is 3 by 3. We know it takes a little bit of time to come up with the 3 by 3 inverse, no question. But now that I have the 3 by 3 inverse, when I perform this multiplication, that's seconds to come up with this guy, seconds to come up with this guy, seconds to come up with this guy, as opposed to solving a 3-variable problem using a matrix 3 times. Now you see the point? Multiplying by the inverse would actually be way faster, way faster. So it's an alternate way of looking at the same thing, but it's actually the path that we just took. That's the huge thing. So I've just shown you this thing here, okay? We don't know what to do with it yet. Not yet. Okay, new problem. I'm going to piggyback on a problem that I did last day. You're going to like this one. All right. Give me a second here. I'm going to use the same problem that I used last day. I just don't remember off the top of my head. All right, so my linear transformation, so we're going to go 4x1 minus 5x2, and then 2x1 minus 3x2. And our non-standard basis will be, we'll go with 1, 1, and 5, 2. Those will be our two vectors. Okay? I want to do this problem from start to finish. Now, I also have a secondary goal in mind. So let's start with A, because that's easy enough. What's A?
4, -5.
Oh, by the way, as part of the process, I need to manipulate this matrix. I need to use this matrix in calculations. So what calculations? Well, at some point in the problem, I'm going to need you to find, a, I don't know. Let's say I need you to find a to the 20th power. I'm just making up an I could go higher. I need this somewhere in the process. Does that seem okay? He's like, yeah, no big deal. But I need you to actually tell me what this matrix is at some point. And by the way, in case you're going, well, I can do that, I'll just keep making the exponent higher. I can make the exponent so high that we're 1,000 years away from a supercomputer that can actually do it. But you're going to do it by hand in like 30 seconds. Wouldn't that be cool? You're going to do this by hand in just well, you get to use a calculator. Yeah. But you're going to do it by hand. I can choose any integer, positive integer exponent, and I'm going to show you how to do this really easily. Whoa. This is a glimpse of where we're going with everything, okay, and the uses of what we're doing. So I got to do the whole rest of the problem now. I have to find A prime, I have to find P, and I have to find P inverse. I need all of those things. Because I can't do the problem without all of them. So, next thing. What is T of V1 and T of V2? Now, we did this last day, so we have some of these results in our notes already. So T of V1, which technically is T of V1 relative to B, by the way, okay, the standard basis, is what? A -1, -1, which we can see is -1 times 1, 1, plus 0 times 5, 2, okay? Which means that T of V1 relative to the non-standard basis is -1, 0. Okay, this looks just like the problem we did. The difference is I didn't have to use any algebra to figure that out. I could just see it. It was right there. T of V2 relative to the standard basis. So 20 minus 10, and then 10 minus 6. We good with that? Again, we've done this problem before. That's not a thing. Okay? So A prime okay, now let's do our P inverse and our P. Because this is 2 by 2, let's take advantage of that. We already know shortcuts. What is P? Those guys as columns. Can you tell me P inverse? So far, so good. All right. Is it possible I did something goofy? A lost sign, or yeah, there's a million, we know there's a million things that could go wrong. So please, at this point, check. I don't know why people they hate checking. I check everything, because I make mistakes. -2/3 plus 5/3, that's 1. 5/3 minus 5/3, that's 0. -2/3 plus 2/3, that's 0. 5/3 minus 2/3, that's okay, good. That's the check. Just multiply it out real quick so you didn't lose any signs or anything goofy. Okay? Now, the third part, I want to do the P inverse AP. All right. Minus 5, 20 minus 10, 2 minus 3, 10 Yeah, you've seen those numbers before. 2/3 minus 5/3, negative 20/3 plus 20/3, negative 1/3 plus 1/3, 10/3 minus 4/3. Okay. We kind of knew that we were supposed to get that. Now, there's a couple of things going on here. I say you check along the way as often as you can. There are going to be problems that we do where we're literally going to start on that board and end up over there because there's so much going on. But most every problem that we look at is going to have built-in checks. Places where we can check up to that point. And every time we perform a check satisfactorily, we can now absolutely assume that everything previous is correct. Okay? Short of just completely going crazy, I'm sure our A is okay. Not positive if my A prime is correct, or am I positive? I mean, can I check these vectors easily enough? Yeah, I know the P was easy, but I might have made a mistake on P inverse, but then I checked my P inverse. So I know again, assuming you didn't just simply write it down incorrectly, that's a not very good error. That's not a very common error. So I checked my P inverse that it was actually correct. I'm pretty sure my A is correct. Can I, and we're going to be doing this, can I literally go from here to here without the in-between step? Do I know this result's going to be correct? If I know my A was correct, I know my P is correct, and I know my P inverse is correct, I don't actually have to multiply to get this. Because we checked them. That's the key. As long as you check them. A and A prime, there's a common misconception that somehow they're related, like they're inverses or something has to happen. No, they're completely different matrices. But because they're similar matrices, they both represent this transformation. That's what is true. They represent this transformation but using different bases. Again, I could just make up bases. I want you to just start cranking them out, okay, Stefan? The rest of the class, just keep cranking out vectors in R2. Just give me 2 at a time. Have some fun. Throw some Mickey fractions, maybe a pi and a root 2 every now and then. Every time we do this problem, we get a different non-standard matrix. And every time we do this problem, it's going to be similar to the original A. Now, does it have any value to us? Not necessarily, but we really like this A prime because it's diagonal. But I still need you to do this. Well, how am I supposed to do that? What does A equal, by the way?
4 -22.
Well, in terms of P and P inverse and all that. Well, what if I multiplied on the left by P? And what if I multiplied on the right by P inverse? Oh, I shouldn't do it here, sorry. Can I say the left side is now A and the right side is now P, A prime, P inverse? Would that be true? Because what's P inverse? What's P times P inverse? Identity. And identity times A is just A. And over here, P inverse is identity. Oh, I have identity, A, identity, that's just A. If A equals, if A prime equals P inverse AP, then doesn't A equal P, A inverse, doesn't it equal this? You notice the P and the P inverse were in reverse order because I had to multiply, get rid of them. So I want to raise this to the 20th power. Well, can't do that quite yet. Not yet. So I'm going to prove some properties. This is our ultimate goal today. Before we leave today, we want to do that problem. All right, so first major proof. N by N, A is similar to B. I want to prove A to the K is similar to B to the K. Tell me about K for this to actually make sense.
Should be a positive integer.
Yeah, K has, you can't take a square root of a matrix or, or a negative. No, K obviously has to be a positive integer, otherwise that operation is not defined. A square matrix can be raised to a power. You did that on your first test. A square matrix, squaring it's no big deal, but it's, word, you got to write them side by side. I want to make this statement that if I have two similar matrices and I exponentiate both of them, that result is still similar. Oh. Okay. So let's suppose It doesn't matter which side I put the P inverse AP on, by the way. It doesn't make any difference. So let's just say B is P inverse AP. Okay? Then what is B to the K? Then it's P inverse AP to the K. Okay? That's pretty exciting. Let's expand that. We do this K times. Okay, great. Matrix multiplication we know is not commutative. But it is distributive, and in this case, more importantly, it is associative. Associative means I can regroup. So that means I can write this as P inverse A, P inverse, A, P inverse, A, P inverse, A, and finally P. Okay. See what I just did? Think of this as a very long sequence. I just grouped the P inverses all the way down the line. How many sets of P inverses do I have? Well, K. I have exactly K of them. So what does this now become? AI, 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 EI, EI, I don't know. Because every time I have an AI, what is that? That's just A. So now what have I got? Oh, how many A's, by the way?
K.
Still K of them. We're finished. B equals P inverse AP. So P and P inverse are transition matrices that show that B is similar to A. Remember, the definition of similarity is there exists a P and a P inverse such that when you multiply on both sides, and by the way, the order, it's not the order you multiply, it's one's on one side, one's on the other. What have I now got? If I took A to the K and I multiply it on one side by P inverse and on the other side by P, I get B to the K. That proves that A to the K and B to the K are similar. That is a very, very powerful proof, by the way. That is one of the more powerful matrix algebra proofs there is. So how does that help us here? What did I want? I wanted A to the 20th. What does that equal? Huh. Okay, well, what was P? This is going to be just terrible, right? So it's 1, 1, 5, 2. And then over here it's negative 2/3, 5/3, 1/3, negative. You know, this way you can use your calculator. And what is it here? Can you perform this multiplication by hand? Yeah. Now, how big is 2 to the 20th? That's a little more than 1,000,000. You can do this with a cheap calculator and a fraction key in under 30 seconds. The entire problem from beginning to end. By the way, should I have any fractions in my final answer? Look at the original question. I'm taking this matrix right here and raising it to the 20th power. I shouldn't have any fractions, should I? Let's do one of these, okay? When I do this one, what am I going to have? I'm going to have this in the first position, this in the second position, and so on. Okay? Then I'm going to take that and do this. And when I do this, this is going to basically undo the fractions. It's going to put them all together. But I'm going to get very large numbers. Okay? Is there a limit to how large a number I can handle? No. In reality, if the numbers start getting too big, what will technology typically represent them as? Scientific notation. Yeah, I don't want to go that big because I don't want to lose the numbers themselves. If you did this on a graphing calculator, it's very, and you have to actually do that to the 20th power, you're probably getting scientific notation in each position. You're probably not getting the numbers. And the numbers are on probably, you know, on the order of 1,000,000 kind of thing. That's not outrageous. So why is this particularly useful? Well, would this work for a stochastic matrix also? Ooh. Yeah, maybe that would be helpful. So one of the first things, raising a matrix to a large power is gnarly. But raising a diagonal to a large power is trivial. There's nothing going on because I'm just raising the diagonal entries. This is just kind of an interesting thing. Okay, walking away from that one. It's not something we're going to do a lot of. I just wanted to expose you to that. If we had done the first problem today, where my non-standard matrix was also just some 2 by 2, nothing special, it wasn't diagonal, I wouldn't want to raise either one of those to a large power, okay, because it'd be a lot of work. But because my non-standard was diagonal, manipulating the non-standard and then using the P and the P inverse to get me back is actually how you're going to do things in general. So if I have my original standard matrix, okay, you asked me the question earlier, this is just so easy to come up with. But if I have to work with this and manipulate this, I'd rather work with this one. The non-standard matrix, the matrix relative to the non-standard basis in general is just another matrix. But this is a specific one because those were special vectors that I used. Every transformation that exists, we're hoping we can find this guy. By the way, it doesn't always exist. Most of the time it will exist, it won't always exist. Yeah, there are bad problems out there. We will do a bad problem. I think a week from today. We will do a problem where there's no answer, just to show you that every now and then, yeah, the bad problems exist, we're going to avoid them, because there's a dead end. But there are times when you can't go very far.
And K is always a whole number? K is always a whole number?
Well, it's this matrix multiplication, so yes.
Okay.
Yeah, that's it. If K wasn't an integer, then the operation didn't exist, right? K can't be negative.
Yeah.
You can't take the reciprocal of a matrix. K can't be a fraction, but K for any positive integer K, including 1. Okay? So that's kind of crazy. Now, I want to, let's see. I'll go to the next one. What do you think determinant now? A is similar to B. I want to look at both of their determinants now. So if we say that B equals P inverse AP, then is it correct to say the determinant of B is the determinant of P inverse AP? Is that legal? Yeah, that's the correct notation. What do we know about the determinant of a product when defined? It's the product of the determinants. Again, they have to be square matrices or this is a moot point. We're not having this discussion unless these are all square matrices. Okay, so it's the same as before. And the similarity has to be square matrices. Otherwise, the P inverse AP multiplication would not exist because you'd have mismatched dimensions. What's this?
Determinant of A.
What's the determinant of P inverse? Well, it depends on what's the determinant of P. No, what is the determinant of P inverse?
The inverse.
It's the reciprocal. That is something we did way, way long ago. The determinant of the inverse is the reciprocal of the original determinant. How do you know that, by the way? Just in general, A times A inverse equals the identity. Because the determinant of the identity is the number 1. Oh, that's why the determinant of A inverse has to be the reciprocal of the determinant of A, otherwise you couldn't get a 1. Okay? The very fact that I'm writing A inverse means obviously there is an A inverse. I'm not saying anything about A. I'm only saying P and P inverse exist. I'm not saying anything about A inverse. Can I go like that? So what have we just proved? Whoa. Not only are their determinants equal, if A is non-singular, then so is B. But if A is singular, so is B. Remember I said before, A did not have to be non-singular for us to have this discussion? A could be singular. It's going to be singular probably half the time. But if A is similar to B, they're both singular or they're both non-singular because they have to have the same determinant. That's kind of cool, isn't it? By the way, we've done a couple of examples so far. Here's my original A. Can you tell me its determinant? -12 minus -10 is
Negative.
-2. Oh, by the way, what's the determinant of this guy? That's not a coincidence, that's what he just showed that. Kind of cool, huh? Similar matrices, it's huge because there's so many things I can do together, okay? So what else is there? Well, here's a good question. A is similar to B, A, B, non-singular. That means they both have inverses, obviously, that exist, that kind of thing. I'm going to assume A and B are non-singular, which would be the same as saying I'm going to assume their determinants are non-zeros. Question. Without doing any work, what's your gut feeling?
Yeah.
Yes. It seems like it would make sense based on what we just did. How would I prove it, though? Let's remind ourselves of something, okay? A, B, non-singular. We're going back to chapter 2. So that means A inverse and B inverse both exist. What is the inverse of the product? Remember, it's the product of the inverses
In reverse order.
in reverse order. And the way you know this is to simply multiply them out side by side. Oh, okay. Again, wait a minute. What do you mean multiply them out side by side? I'm going to show you how you know it's in reverse order. There's a simple proof to this. If I took AB and I multiplied it by AB inverse, do we agree we get the identity? If I take AB and I multiply it by B inverse A inverse, what do I get? That's the proof. It's actually that simple. Sometimes we forget that proofs can be really, really easy. A lot of the algebraic proofs involving matrices usually are simple. I've just done some absolutely astronomically important proofs so far today, and all of them were pretty easy algebra, weren't they? There was nothing conceptually difficult. I didn't have to go out on a limb. I just proved to you, we already knew this. I've done this way, way back when. But I just proved this by just simply multiplying it out and showing you get the identity. And if I multiply two matrices and get the identity, they have to be inverses. That's what it means. So, let's start somewhere. So we'll write the proof. Suppose B equals P inverse AP. I got to start somewhere. Let's take the inverse of both sides because the inverse does exist. If this statement is true, then does B inverse equal P inverse AP quantity inverse? Is that true? Two things are equal, and I just took the inverse of both of them. Is that still, are they still equal? I haven't actually done anything yet, folks. I just wrote it. Yes, if this statement is true, then this statement has to be true because B inverse does exist. So now let's manipulate the right side. I'm starting by making this supposition. I have to start somewhere. I'm assuming, I told you A was similar to B, therefore one of them equals P inverse, times the other guy kind of thing. So I said, let's just suppose it's that way. I could have done it A equals and it wouldn't have made any difference in the final thing. Let's now expand this. The inverse of a product is the product of the inverses in reverse order. So what does that look like? P inverse, A inverse, P inverse, inverse. Wait, what's P inverse inverse? Now what? We're done. What have I got? B inverse equals P inverse A inverse P. Whoa, that was easy. Almost too easy. If two matrices are similar, Their determinants are the same. So they're both singular or they're both non-singular. If they're both non-singular, we just proved then that their inverses are also similar. Either matrix raised to a power is similar to the other one raised to a power. So there's a whole lot of stuff going on here. There's still more stuff. Any questions so far? This is kind of wild stuff. The reason, again, I'm sticking, on the examples I'm sticking with 2 by 2s just so we can navigate through the algebra, because you understand the concept of changing bases. You understand the concept of writing a vector in terms of another base, and it can be really busy. The next quiz, I've given you one problem, basically. I said, here's a transformation from R3 to R3. And I've asked for and I've given you a non-standard basis. So I asked you for A and for A prime. I've asked you for P and P inverse. I've asked you to demonstrate that A and A prime were similar. So you perform the multiplications. Then I gave you a vector, and I said, now let's run the vector through and show all the things. So that's something we haven't done yet. So let's just take a random vector now. Because that's the one thing we haven't done yet. In fact, I'm going to do it not for this one. I'm going to do it for one that's not as happy as this. Okay? So let's think of a new problem. I'm going to fill my time here. So we end at 3, is that right? Sometimes it feels that way, I know. All right, so let's say this is x1 plus 3x2, 2x1 minus x2. And let's say that b prime is, how about 1, 2, and negative 1, I don't know, 3. That seems reasonable. I'm just making it up. All right, call that V1, we'll call that V2. Now, I'm going to have a vector out there, we'll call it W. And W is going to be, I don't know, how about 2, 1. I want to do all the things we just did. I want to find the A prime, the P inverse. But then I want to use W and show how it gets manipulated by the standard and the non-standard and how you justify things. Okay? So you should be able to go fairly quickly. So A, okay? Now this time, we'll do, but let's use the inverse matrix this time because we found that can be really fast. So first thing we're going to do, let's find T of V1, which automatically makes it T of V1 relative to the standard basis. So what is this going to be? And in fact, I'm going to do it this way this time, just to save some time. So what's this?
7,
1 plus 6 is 7.
1. Or negative.
And
Negative. Wait.
hold on. 2 minus, isn't that 0?
0.
So 7, 0. And then T of V2, negative 1, 3, so that would be 8. Negative 1, 3, that'd be negative 5. Okay? Yes? Okay. We're not going to solve it like we did before. We're going to just go directly. I'm going to show you what we're going to do. What's going to go here? P inverse. So this time I'm not even going to bother solving it algebraically. I'm just going to go ahead and go straight to P inverse, which means we've got to find P inverse. Okay, so I want to find my transition matrix. So 1, 2, negative 1, 3, 1, 0, 0, 1. I know we can do it the other way, but I want to do it the regular way because that's what you're always going to do when it's 3 by 3. There's no shortcut, so we just want to remind ourselves of the process. Yes, it's a 2 by 2. I know there's a shortcut. Absolutely, there's a shortcut. All right, so negative 2 of those, negative 2 of those, negative 2 of those. Let me take 1/5 of that row. And then finally, row 2 plus row 1. So boom, boom. Okay, so it appears that P inverse is 3, 5, 1, 5, negative 2, and 1/5. What is P? I'm pretty sure that my P inverse is correct, so we'll keep going, right? I'm winking with my left eye, so you know something's up. Now, what are we doing next? I'm checking. Yeah. I sometimes have to hit people over the head with a blunt object. Oh, you gotta check. I might have made a mistake, no matter how easy this is. As I maintain, the smartest person in the class is still only going to get 95 out of 100 correctly. We're still going to make typos occasionally. You just don't know when they're coming. 3/5 plus 2/5, negative 3/5 plus 3/5, okay, negative 2/5 plus 2/5, positive 2/5 plus 3/5. Okay, I'm good. The reason why that was so important is because now is that right? 1/5, 1/5? Okay. Yeah, make sure I wrote it down correctly. So what do I get? 21 minus 0, so 21/5, negative 14. And then here, 24 minus 5, so 19/5. Negative 16 minus 5, so negative 21/5. Okay, now how would I do a check? I would say 21/5 times 1, and then plus 14/5, that's 35/5 or 7. Then 2 times 21/5 is 42/5. Minus 42/5, that's 0. Okay, I just checked it. Yeah, I just took, that's C1 and C2 in my vector. So I said C1 of these, C2 of these. Okay, and then the second one, same thing. 19/5 times 1 plus 21/5, that's 40/5 or 8. 19/5 times 2, that's 38/5. Minus 63/5, that's negative 25/5 or negative 5. Okay, we knew it was going to work. I still like to check. And I like to show you how the check is done. So what is A prime? It's a factor. 21. Does this look right? I'm just standing too far away.
Yep.
We have our P inverse, and here I also know this thing. So P inverse AP is in fact going to equal A prime. How do I know that? I didn't check that. Well, actually I checked that P and P inverse were both correct, and then I just checked that these were actually the vectors of A prime. In theory, this is absolute. There's no exception. I know that's true, I know that's true, I know that's true, and I know what that one looks like. Do I physically need to perform the multiplication? Actually, I don't, because I checked all the pieces beforehand. So there's sometimes you can actually skip, yeah, go ahead and multiply it out. But you don't have to now because we already know what this is, and we know that that has to be equal. Now, where does W fit in? This will be the last piece of the puzzle today. I want to write W, I want to find T of W. That makes it automatically relative to the standard basis. Then I want to find T of W relative to the non-standard basis and show it how we justify all this. And also how we can come up with it. Do I have? Hold on, did I write this anywhere else? I'm going to go ahead and put my P and my P inverse over here, because I need the white space. Okay. So my P and my P inverse. When you're doing these on paper, you don't have to rewrite them at all. I just have to keep erasing stuff. Now, let's find T of W, which automatically makes it relative to the standard basis. So what's T of W? 5. Yeah. And like before, here's where it's absolutely practical to write this as a column vector, or column matrix rather than vector, because we're doing matrix multiplications all over the place. Today in my 116, I'm introducing matrix multiplication, how to find the inverse of a square matrix, and solving a system using that inverse, using multiplication. Wish me luck. These are people that swore last day when we did matrices for the first time that they'd never even heard the word. Problem is you can't be in college algebra without having had intermediate algebra, and they spend a month in intermediate algebra on, well, matrices. So, and then we did the addition problem. You know, here's two linear equations, you know, two variables. So you add them to eliminate a variable. And I was working with someone who said, I've never seen this before. I said, I find it hard to believe. Why? Because I go, you do this in pre-algebra and elementary algebra and intermediate algebra and now in college algebra. I find it hard to believe you've never seen this. Not remembering is one thing, but I've never seen it. I just have a hard time with that one. It's like, couldn't have gotten this far with every single class skipping all of the work. But I don't know, maybe. All right, so I would like to, this is relative to the standard basis. How do I find this? Well, one way of doing it, the way we did it before, was take 5, 3, and write it as a linear combination of these guys. And by the way, because we're in R2, that's just not that hard, is it? Is there another way? How about if I multiply by P inverse? Why is that going to be the easiest way at this stage of the game? Because we already have P inverse. Yeah. I already got it. I might as well use it. Yes, you can, absolutely, you can solve the system. That is correct. And knowing that I'm supposed to get the same answer might be a heck of a lot easier just doing this. And here's one of the reasons we like this process in general is because this, it doesn't matter whether I was working with ugly or nice at this point. This is still the same step. I'm still multiplying by the P inverse. P inverse is never going to be happy and simple. P inverse is never going to be diagonal. No, that's never going to happen. It's what it is. I mean, probably fractional. And so I'm multiplying this by 5, 3. Let's see, what do we get? 15 minus 3 is 12 fifths. Negative 10 plus 3 is negative 7 fifths. Did I mess it up?
15 plus 3 is...
Did I? Oh, thank you. 18 fifths. Like I said, we make errors, don't we? By the way, you notice how I included all of you in that one. We make errors. No one of us makes an error. We share. Okay, so what is this? What did I just give you? I gave you a vector relative to some non-standard basis. I'm pretty sure I did it right. What do these numbers represent? In terms of a system of equations, they're my C1 and C2, aren't they? They're the coefficients of something. The coefficients of what? Very specifically, the coefficients of V1 and V2. Here's what I think that I just said. Like this. I think that I just said 18V1 minus 7 fifths V2 is meaningful somehow or another. I think that's what I just said. So let's do that. So that's 18 fifths times 1, 2, minus, and I'll do this in vector form at this point. There's no problem with that. Negative 1, 3. By the way, do I care about the 2, 1 anymore? No, 2, 1 was my pre-image. I'm only interested, I'm doing images now. But I did an image relative to the standard basis, and then I have another image relative to the non-standard basis. How do I know that I'm doing everything right? Well, assuming that I didn't mess this up. You understand, if this is incorrect, then everything that follows is also incorrect. So make sure that that's correct. When I do this, what do I get? So 18 fifths plus 7 fifths. What's 18 fifths plus 7 fifths? That's 25 fifths, or 5. 36 fifths minus 21 fifths is how many? 15 fifths, or 3. What does this mean to me? Does that make sense? we took the image relative to the standard basis. By multiplying it by the transition matrix, we got an image relative to the non-standard basis. How do I do it? I did it right, because those are the coefficients of the non-standard basis. And when I ran them through there, so had I asked you to do it this way, do C1 of these, C2 of these equals this, you would have set up a matrix and you would have solved that matrix and you would have got 18/5 and -7/5. We also know that using an inverse would have done the same work in about the same amount of time. But a lot of times we do all these processes, but we don't know where the numbers actually go. What did we just find? So let's step back now. What do we got? Starting with a linear transformation. There is no system of equations. There is a linear transformation. This is essentially where matrices come from. Okay. Matrices are born and they're bred here. I can use them for other things, but the matrix comes from this linear transformation. And I have potentially any number of non-standard bases. Every non-standard basis I have will produce a different non-standard matrix, and they're always found the same way. By taking the vectors, running it through the transformation, and then writing the result as a linear combination of the vectors. We can go non-standard to non-standard. That's an interesting problem. It's twice as much algebra, but we're never going to use that in the future, so I'm staying away from that right now. That problem is a little gnarlier. That we have the first non-standard basis, we run the vector through, and then we write the result as combinations of these guys, and which makes all of the rest of the stuff sometimes a little harder to interpret and follow. So I'm staying away from that one today. So, trivial, a bit of work. Trivial, a little bit of work. Ultimately, P inverse AP, and by the way, the order of the multiplication has to be correct, because P inverse was the transition matrix from standard to non-standard. A was the standard basis. So that's why what does P inverse do? That converts me to the different basis. That's why it's P inverse times the guys in A. Oh, that should make some sense. Okay, any questions so far? There's a lot of stuff today. Everything we did today we're going to continue to use, but the big difference is on Wednesday, we're going to learn how to select the basis that we want. I'm making these up off the top of my head. I'm just making up randomly. But we know there was one particular basis that worked beautiful. But do all bases work beautifully? No, generally only one of them is going to work nicely. So we're going to learn how to figure out what that basis is. Question?
This problem, W was provided, right?
Yes. I started with saying, because we'd like to see what happens when I have a vector. This is an input-output machine still, right? Think of this like a big old gnarly function. So I'm inputting vectors. We've been inputting only the basis vectors, but what if I just grab a vector at random from the world? Oh, that vector at random from the world can be written as a combination of the standard basis or a combination of this basis. So that's kind of important. Now, one that we did not do. Can I write 2, 1? Can I write the vector 2, 1? There's one more thing I want to show you that I have not done yet. I want to find, now we did not do this, okay. There is still one more piece. I was looking at the clock going, why did I leave a couple more minutes? Now I remember. Everything we said is valid, it's true, it's correct, it's useful. But now here's what I want to do. I want to find T of W using A, and I want to find T of W relative to B prime using A prime, meaning I want to actually physically perform the matrix multiplication. Well, the first one's easy. What's the first one? The first one is, what was it, 1, 3, 2, negative 1. And then this was 2, 1. So 2 plus 3 is 5. 4 minus 1 is 3. Okay, we already knew that. But we did it by running it through the transformation. And now I want to do it as a matrix multiplication. So now I want to do this one. So here's the question. Uh, 21/5, 19/5. What are the other two?
-14 and -21.
I never would have saw the -14. And negative or positive? Right?
-21.
Okay. What goes here?
2, 1.
Are you sure? What is A prime dealing with? Isn't A prime dealing with things relative to the non-standard basis? But isn't 2, 1 relative to the standard basis? If I put a 2, 1 here, I'm not going to get the right answer, folks. Am I? I need to put something here where my final answer is what? I need that to be my final answer. Oh. This was P inverse times T of V, or T of W. I want to do A prime times W. But this W has to be W relative to B prime.
Right.
Does everybody see that? Because this is the matrix relative to B prime, this vector has to be relative to B prime. They're from different universes. Oh, so I need to write 2, 1 as C1 of these, whoops, plus C2 of these. Well, how the heck can I do that? Well, I'd set up a system of equations. There's an easier way. How about W relative to B prime? Isn't that just P inverse times W relative to B? Wouldn't that be easier? By the way, your alternative is to solve the system, which is always correct. But now we realize that's always the most amount of work. It's not, the inverse isn't the most amount of work. Once I have the inverse is usually the least amount of work. So what will this be? This is the last piece of the puzzle you needed to see. 3/5, 1/5, negative 2/5, 1/5, 2, 1. And what does that give me? 6 plus 1 is 7/5. Negative 4 plus 1 is negative 3/5. So let's see if this works. Get out your calculators, please. 7/5, negative 3/5. So I have 147 minus 57, that's 90 over 25, which is 18/5. That's a good start so far. Negative 98 plus 63, that's negative 35/25, which is negative 7/5. Not trivial, but the way it goes. So do you see how many different things that we accomplish? We're just sort of going around. We're using the same things over and over. The universal error that we make, this is trivial. This is the easiest thing I could possibly ask. Here's a vector. You know the standard matrix. Multiply them. Can't miss this one up. You figured out the non-standard matrix, but you can't use that vector because this vector lives in standard basis world. I need a vector that lives in B prime basis world. Oh, and now, but these vectors don't look anything alike. No, because this is the vector relative to B prime. And what did we just do a moment ago? We just justified by multiplying it out that it is the same thing. When I use those two values as coefficients on these two numbers here, we got that guy back again. That's how we know. That's why you've got to do the checks. Because if you made an arithmetic error anywhere along the line, the whole thing kind of falls apart. So as we check as we go, everything's confirmed. Okay? All right, go ahead and stop. This is, there's a, I don't,